Hi everyone, the subject for this video is dimensional analysis. Dimensions can be multiplied, divided, or raised to powers. Quantities can add or subtract only if their dimensions match. For other functions, both the input and output must always be dimensionless. And dimensional analysis can be a powerful check on your work. It's not going to be something that I heavily emphasize in this semester, but I encourage you to use it all the same. It could mean the difference between getting an A or a B in this class, quite honestly. Okay, so what are dimensions? What am I talking about here? In an introductory physics class, there are just three fundamental dimensions: length, time, and mass. That's it. There are other fundamental dimensions to be introduced in other classes. So in particular, in the second physics class that you ever take, the course covering electricity and magnetism, you'll introduce either charge or the rate of flow of charge, and that is going to be taken as a new fundamental dimension. But the only ones that you need to know for this class are length, time, and mass. And there are non-fundamental dimensions that can be written in terms of these three fundamental dimensions, and we'll talk about those later in this video. So to denote the dimensions of a quantity, we can write, for example, we put brackets around the quantity in question. So I have some quantity x, and it has dimensions of length. We put what looks like an equal sign between these two things. It's not an equal sign. It's not an equation. It looks like one, but an equation to me is something that you can plug numbers into. And this is saying, in words to me, the dimensions of x are length, okay? But there's no number that we can plug in for L. L is not a variable, and likewise, this quantity in brackets over here is not a variable. It's just saying the dimensions of whatever's inside are length. So I'd like to get that out of the way. If it were up to me, we would use an entirely different notation that would exclude this equal sign, which is not really supposed to be there. So I'll try and tell you where that could trip you up a little bit later. All right, so let's talk about multiplication and division. Any quantities can be multiplied or divided. You could just always do it. There's nothing stopping you. Their dimensions will also multiply or divide correspondingly. For example, we know that speed is a distance traveled over a time interval, and so we can write the dimensions of v, if v represents our speed, is the dimensions of distance over time, distance traveled over a time interval. And you are free to break up the brackets like so. So like I said, the dimensions that go into the calculations also multiply or divide correspondingly. And so that's what I've done, is I've taken the dimensions of x over t and said that it's the dimensions of x divided by the dimensions of t. And distances we know have dimensions of length, and time we know has dimensions of time. And so, taken in full, the dimensions of v, our speed, are length over time. Not an equation. The dimensions of v are length over time. Note that the fact that velocity, or I should say speed, we'll talk about velocity a little bit later. So note that the fact that speed has dimensions of length divided by time is consistent with the units that we use in writing speed quantities, such as miles per hour. So if you're driving down the street at 30 miles per hour, how is that consistent with what we've just written? Here's miles per, divided by is per, and t is hours. So length divided by time. So the units that we use are consistent with the dimensions that we use. Dimensions can also be raised to powers. They can be squared or cubed or even square rooted. For example, if I investigate the volume of a box, I know that it will have dimensions of, now I'm using capital V for volume. So the dimensions of V will be the dimensions of I can measure it, for example, as length times width times height. Once again, I can break up those dimensions individually. Dimensions of length times dimensions of width times dimensions of height. Well, that's a length times a length times a length. Each of those would be measured with a ruler, and so they're all lengths, which is length cubed. Okay. So you might measure volume in meters cubed or centimeters cubed, feet cubed, something like that. But the point is that it's a cubed length. All right, here's a kind of non-trivial example. Suppose that I'm painting a room and I'm interested in the rate at which I paint. What would be the dimensions of this quantity? Well, I'll call the rate that I'm painting R. And I'd like the dimensions of R. And how might we characterize R, the rate at which I'm painting? Well, let's characterize it. Go ahead and pause the video. Think about this for just a second on your own. But the way that I would characterize R, the rate at which I'm painting, is how much area I've been able to paint in a particular time interval. So if I'm able to paint, I don't know, an 8-foot by 10-foot wall in 15 minutes, we would expect that I would be able to paint an 8-foot by 20-foot wall in 30 minutes, something like that. Okay. So I'm going to say that it's an area divided by a time. So the dimensions of R are the dimensions of area divided by time. Well, what's area? That's width times height. It's another way that we can write that. And let's break up these dimensions now. Dimensions of width times the dimensions of height divided by the dimensions of time. And that's a length times a length divided by a time. Sorry, that should be capital T because it's the dimensions of time. Notice that's no longer in brackets because these are the dimensions themselves. And so we finish it off by writing it as length squared divided by time. Okay, so there's my dimensions of how fast I can paint. So if I'm describing how quickly I can paint the room, I might measure that in something like meters squared per hour or feet squared per minute, something like that. Quantities can be dimensionless. So when all of our factors of length, time, and mass cancel, we denote the resulting dimension as 1 and call this a dimensionless quantity. For example, the number of milligrams of poison per kilogram of body mass that results in the death of 50% of specimens is called the LD50. This is an actual term. You can go ahead and look it up, LD50. So what are the dimensions of LD50? Well, the dimensions of LD50 are, it's the number of milligrams of poison per kilogram of body mass. So it's the mass of poison divided by the mass of body. Let's break those up again. M poison, dimensions of mass poison divided by the mass of the body, or the dimensions of the mass of the body, which is the mass divided by mass, which we rate as 1. Okay, so that's saying that the LD50 is a dimensionless quantity. So because LD50 is a mass of poison divided by a mass of body, it is a dimensionless quantity. All numerical constants, so for example 4, 1/2, pi on the square root of 5, are all dimensionless. We'll talk about addition and subtraction. Quantities can be added or subtracted only if their dimensions match. So it makes no sense to say 5 feet plus 12 seconds. You can't add a length and a time interval. That doesn't make any sense. For example, we will later define velocity as the change in displacement, which has dimensions of length over a time interval, and that'll give us the equation v equals x2 minus x1 over t2 minus t1. So its dimensions are, dimensions of v, put it a little bit higher, oops. Dimensions of v are the dimensions of x2 minus x1 over t2 minus t1, which are, we'll break this up slowly, dimensions of x2 minus x1 divided by the dimensions of t2 minus t1. And we can break up these brackets correspondingly. Dimensions of x2 minus the dimensions of x1 divided by dimensions of t2 minus dimensions of t1. Let's put this on the next line here. Okay, here's where it gets tricky. Okay, we're going to substitute in dimensions of x2 are a length, dimensions of x1 will be a length, so L minus L, divided by dimensions of t2 is time, and dimensions of t1 are time. Here's why it's tricky. This is not an equation. We have equal signs flying around everywhere, and it looks like an equation, but it's not. You're going to look at this and you're going to think L minus L, well, that's 0. T minus T, well, that's 0. But these aren't numbers. These are dimensions. And so what you really want to think about here instead is to say a length minus a length is another length. A time minus a time is another time. And so we actually get a length in the numerator and a time in the denominator. Okay? So that's the answer. You'll notice that it has the same dimensions as speed. If you're not already familiar with velocity, it has the same dimensions as speed. What about other functions? How about a trigonometric function? Cosine of theta. What about exponentiation, 2 to the u? What about logarithms, the log of a? What I'll say is that theta is dimensionless. And cosine of theta is dimensionless. For 2 to the u is dimensionless. Oops. And 2 to the u is also, whoops, I don't know how that became a 4. 2 to the u is also dimensionless. And for log of a, shouldn't be too much of a surprise at this point, a is dimensionless. And the log of a is also dimensionless. In each case, both the function and its argument, so what goes inside the function, are both dimensionless. In general, any function that isn't addition, subtraction, multiplication, division, or a power must have both a dimensionless input and output. So don't forget that square roots are fractional powers, and so they can have dimensions. So you can take the square root of a dimension quantity. By the way, in each of these examples, each of these previous examples, I use just a simple single variable. Maybe I'll have 2 variables in there. So it's common in physics to talk about the cosine of omega times t. That pops up a lot in physics. In this case, t will have dimensions of time, but collectively, whatever is inside this cosine function all has to be dimensionless, and so omega, we therefore know, must have dimensions of 1 over time. So to write that out explicitly, the dimensions of omega t are equal to the dimensions of omega times the dimensions, oops, just rewrite that. So the dimensions of omega times the dimensions of t. And so this is the dimensions of omega times capital T, our dimensions of time. And we know that that must be a dimensionless quantity. And so if I were to rearrange that, if I were to divide both sides by the dimension of time, I would derive that the dimensions of omega are 1 over time. Okay. And that is true. Why do I want you to know all of this? Well, primarily, dimensional analysis is a very useful tool for checking your work. So suppose you finish a physics problem and you find an expression for a desired quantity. Well, you can check your work by making sure the dimensions of both sides of the equation match. If the dimensions don't match, you have certainly made a mistake. I guarantee that you have made a mistake if your dimensions do not match and if you've done your dimensional analysis correctly. If the dimensions do match, your answer may still be incorrect, but it is at least plausible. Okay? Having the dimensions match doesn't assure you that your answer is correct. You could, for example, be missing like a factor of 2. You may have forgotten to add a term. It is possible that you've made a mistake. But if your dimensions don't match, something has gone horribly wrong. All right, here's an example. This is a little bit of a contrived example. It's not entirely unreasonable, but it's not something that that corresponds to a problem that I have in mind. So late in the semester, we will discuss power, which has dimensions of mass times length squared divided by time cubed. Suppose you are trying to derive the power for some physical system, and you find capital P is equal to the quantity m over t times the square root of gx minus 2f times v. This is not not an especially difficult expression that I've derived here, not an especially complicated expression. You will deal with expressions that are just this complicated and even more so before the end of the semester. Capital P is power. The dimensions of m are mass, the dimensions of t are time, dimensions of g are length per time squared. That's actually an acceleration. Dimensions of x are L, length. Dimensions of f are mass times length divided by time squared. And the dimensions of v are length divided by time. Is your derived expression possibly correct? Well, let's find out. So I'll find the dimensions of p, and that's the dimensions of mass divided by time, or m divided by t, square root of gx minus 2f, that was in parentheses, times v. So dimensions of all of this on the right-hand side. We hope that the dimensions on the left-hand side match the dimensions on the right-hand side. The way I have it in my notes and the way that you can do this, I've broken it up such that I take the dimensions of each of these multiplied quantities and then basically slowly work the brackets in until they appear in all of the quantities. But I'm just going to skip all of those steps because just in general you could just put brackets around everything individually, and it's equivalent to the to going through and deriving them tediously. So every variable now gets brackets around it. I'll put brackets around the 2. Okay, so the dimensions of power, we hope, are the dimensions of m divided by the dimensions of t times the square root of the dimensions of g times the dimensions of x minus the dimensions of 2 times the dimensions of f times the dimensions of v. All right. If you look at go back on to the previous page on the video, we can look at what each of these were. Dimensions of m were mass, dimensions of t were time, dimensions of g were length divided by time squared, dimensions of x were length, we square root those. Dimensions of 2, well, it's a constant, it's a mathematical constant, so it's dimensionless. Dimensions of f were mass times length divided by time squared, and the dimensions of v were length divided by time. Mass times time times the square root of length squared divided by time squared, minus 1, well, dimensionless quantities don't affect anything else, so it's mass times length divided by time squared times length divided by time. And, oops, So I had time squared here. I have to make sure that this is squared in the denominator here. Okay. And we get mass divided by time times length divided by time, because we square root those squared quantities, or squared dimensions. And I see a mass times a length divided by a time squared, and it's being subtracted. Get mass times length divided by time squared times length divided by time, and I get mass times length squared divided by time cubed. I look back on the previous page, and I told you that power has dimensions of mass times length squared divided by time cubed. And we just derived that it's mass times length squared divided by time cubed on the right-hand side, and so these dimensions match. So this is good. It means we've done well, that means that we haven't done our problem entirely incorrectly. It doesn't mean necessarily that we've done the problem correctly. But the point is that, yeah, we were hoping to get the dimensions of power on the right-hand side to match the left-hand side. So maybe to be a little bit more explicit, I could have made this substitution immediately. Mass times length squared divided by time cubed. If at any point we had tried to subtract two quantities of different dimensions, or if our result had been anything other than a mass times the length squared divided by a time cubed, we would know that we've done the problem incorrectly. All right, I'm going to close out this video by just listing different dimensions that you'll encounter in this course. There's distance and displacement, both have dimensions of length. Time has dimensions of t, or time. Mass has dimensions of mass. Those are the fundamental quantities. I've already introduced you to them, and you should already be familiar with them. Speed or velocity has dimensions of length divided by time. Acceleration is a length divided by a time squared. Force is a mass times a length divided by a time squared. Momentum is a mass times a length divided by a time. Energy and work are both mass times length squared divided by time squared. Power is mass times a length squared divided by a time cubed. Pressure is a mass divided by a length times a time squared. And I'm looking over this, I realize that I've omitted torque. So let me squeeze that in here. Torque is a mass times a length squared divided by a time squared. And so you'll notice that it has the same dimensions as energy and work, but it is a distinct quantity. It's its own thing. All right. These and other dimensions can be derived with any equations involving these variables. Well, except for the three fundamental dimensions. Those can't be derived. But any of these other ones can be derived using equations involving the variables. So I'll give you an example of that. We will, at some point, write F equals ma. Force equals mass times acceleration. So let's use that to find the dimensions of force. We'll pretend that we don't know what the dimensions of force are. That's the dimensions of mass times acceleration, or the dimensions of mass times the dimensions of acceleration. And so if you don't know the dimensions of force, as long as you know the dimensions of acceleration, and of course the dimensions of mass, then you can take those and multiply them together, and the dimensions of mass are mass, and the dimensions of acceleration are length divided by time squared. And so I know that the dimensions of force are therefore mass times length divided by time squared, just from the equation F equals ma. And go back up, and we see that force is in fact a mass times length divided by time squared. So you won't have to memorize all of these. You should memorize other physical equations, but in case you want to have your dimensions at hand, if you want to have them available to you throughout the semester, here they are. Here's most of the dimensions that we'll work with. And there's other quantities that we'll work with that have other dimensions as well, but you can derive those yourself. So please use dimensional analysis, especially as we did in this example problem here, throughout the semester to check your work. It can be a very valuable check, especially as you go along before you find your final result when doing a problem. Okay, so good luck and use it throughout the semester. I hope it serves you well. Bye-bye.